Lightning can be awesome in its power to amaze us, devastating in its power to destroy. Each year, lightning claims hundreds of lives, causes over $100 million of property damage, and starts more than 10,000 fires. In March 1986, just after launch, an unmanned NASA rocket was struck by lightning. The loss, over $160 million. Part of lightning's power is its unpredictability. We never know where or when it's going to strike next. But we're starting to learn. A new, highly accurate system of lightning detection records the exact time and place of a lightning flash. This information is transmitted instantly to a central computer at the Environmental Research Laboratory's office in Boulder, Colorado.
Severe thunderstorm in progress or developing, and this is the Denver area right in here.
Meteorologists can then track the direction and intensity of storms. In addition, large quantities of lightning data are recorded for later analysis.
When we first started to get the data, we were overwhelmed by the amount of these data. In the past, researchers had been looking at just a handful of lightning flashes, maybe over several years, 100 or 200. And here we collected, in 1 year, we collected 750,000 flashes in just a limited area here in Colorado. So we were overwhelmed. I said, well, what do we do with it? So the first thought was, well, where does it occur? When does it occur? And how much?
The challenge for Raul Lopez and his colleagues was to make sense of these numbers, to try to organize the data in a way that would reveal a pattern in when and where lightning occurs.
Without a tool for extracting the main regularities and the main patterns in the data, we would be lost. So statistics is extremely important in our work.
The first and simplest technique that Raul Lopez used to organize the Colorado lightning data was a picture. He made a histogram, a special kind of bar graph. Here's how he went about it. The horizontal axis represents time of day, divided into hours. The vertical axis depicts the number of days on which the first flash of lightning occurred at a given time. If the first flash was between 11 a.m. and noon, for example, we enter a block for that time of day in this column of the histogram. As the histogram bars build up, we find the surprising picture that appeared to Lopez. The overall pattern, or distribution, of first flashes shows a peak between 11 a.m. and noon. In fact, that's when the first flash happens on 1/3 of the days. The histogram displays a good deal of other information. The distribution of first flashes is lower outside the 11 to noon column. The height of the bars falls off sharply, clustering around only a few hours on either side of noon. And the fall-off is roughly symmetric. It slopes down evenly into both morning and afternoon hours. The key results can now be stated clearly. Amazingly enough, lightning storms never began at night. Instead, lightning almost always began within 2 or 3 hours of noon. Lopez and his colleagues then looked at the time of day when the maximum number of lightning flashes were recorded. They found a similar pattern, a peak showing that most days had the maximum number of lightning flashes between 4 and 5 o'clock in the afternoon, with a narrow spread of a few hours on either side. But this time, there were a few cases where the maximum rate was not achieved until the early hours of the morning. Observations like these, which stand apart from the overall pattern of the distribution, are called outliers. But the few outliers don't detract from the overall pattern of the lightning data. Such striking regularity fueled the curiosity of the researchers.
The interesting thing about these histograms showing the clustering was that, look, there's something regular here, something that tends to occur very frequent during the summer. A lot of these days, the first flashes are tending to occur at a given time. Immediately you ask, well, why? Why is that? Why is that? And the thing is that here in this mountainous region, the topography induces some circulations. And because of the circulations, you have areas where clouds are formed more than in others, and at sometimes more than in other times.
We can understand this regularity better by looking at the unique topography of Colorado. During summer afternoons, the wind carries warm, moist air from the eastern plains toward the Rocky Mountains. Once it hits the mountains, this warm air is forced upwards, where it mixes with colder air higher in the atmosphere to form storm clouds. These summer wind patterns influence when and where lightning is likely to occur. This is a description of local weather patterns, but larger weather systems can also influence the occurrence of lightning and help explain some of the outliers observed in the histograms.
When you look at the distribution of the maximum activity, you notice that there are some that were not clustering at all, but were occurring far away from the center. You immediately tend to think about outliers and why. Those are days where you have a very strong control by your weather systems. You might have had a late front coming in during the day or a very early front coming in during the day, and overpowering the local influence, this influence that comes over and over every day that determines the clustering around a particular time.
All the lightning strikes are all concentrated in one area.
You can actually use
the discovery of lightning patterns in different regions of the country continues to grow. Does this mean that lightning, which has seemed so dangerously random in the past, is now predictable? It's a little early for that conclusion.
I don't think we're at a stage where we can say that we can predict lightning, especially when it comes to predicting where it would actually hit. You see, that's a very major problem. But I think we're in a position now where we're starting to learn what are the factors that determine if a day is going to have a lot of lightning, little lightning, or be in between. I think we're at a position now where we can start saying, well, if we're going to have some lightning, it's probably going to be occurring in this region of the mountains, and around the peak activity is going to occur around this time.
The striking feature of a shape like this is the symmetry. A distribution is symmetric when the two sides are mirror images of each other. Now, the morning half of the Colorado histogram is not exactly the same as the afternoon half, so this distribution is just approximately symmetric. Actually, perfect symmetry in real data is highly unusual. This unique photograph was made years ago at Pennsylvania State University. Women undergraduates were lined up by height categories. This living histogram also shows a high degree of symmetry, and you'd find a similar pattern for height in almost any particular population. Another important aspect of a distribution is where its center lies. In Colorado, the first flash of lightning on any given day was most likely to happen around noon, and this fact shows up in the histogram, where noon stands out as the center of the picture. Finally, after identifying the shape and center of a distribution, we look for deviations. Sometimes these deviations are outliers, individual observations which don't adhere to the overall pattern. Lopez explained these outliers in the lightning data by incorporating more global weather patterns into his theories. In other contexts, an outlier may be trying to tell you something about the measurement you're making. An unusually high score on an aptitude test, for example, may reveal a student's hidden genius or a defect in the design of the test. Of course, there are other less glamorous possibilities. Outliers are often the product of equipment malfunctions or of typos while entering data. The point is, you have to try to figure out what caused an outlier. Only then can you decide how important a part of the big picture it might be. Deviation, center, and shape are all important things to know about a distribution. So far, all we've seen are symmetrical distributions. In fact, we find all kinds of distribution shapes. As we'll see, non-symmetric distributions play an important role in determining which programs you get to watch on television.
On the next MASH.
I am sex itself, gentlemen. I am life. I am appetite.
And I'm not taking my clothes off till he leaves.
Old situation comedies,
Thursday, Diana Ross is
Billie Holiday, that's my name.
Gotta make me,
classic movies,
Middleton in front. Janney with it, coming in. Score!
local sports coverage. This is typical fare for primetime programming at an independent station like Boston's TV 38. Behind this lineup is a strategy called counter-programming. Since Channel 38 cannot afford to produce programs that compete with the networks for the same audiences, they look for alternatives.
As we like to say, we want to zig when the other guy is zagging. So that's our way of counter-programming. When the networks are running Cosby and Cheers and all these shows during the week, we may have a hockey game on against it. Altogether different audience. Or a movie, another alternative. And that's basically what we mean by zigging and zagging.
You take into consideration who your available audience is, who's watching TV at that particular time of day. Then you take into consideration what your competition's running, what types of programs they're airing. Then you also take a look at the type of advertisers, what is their target demographic. And you kind of put that all together in the mix along with your program schedule to see, to look at the flow of the schedule and all of those elements. 54% of Trapper John's audience are women 18 plus, 31% are men 18 plus.
The key to counter-programming is knowing who watches what. For that information, Leslie Savage turns to Nielsen Ratings Service, which not only measures how many people watched a syndicated show when it aired on the networks, but also who they were, their sex, and their age.
Over the demographics of who is watching the program. All right, so let's take a look at Punky.
Here, Leslie is analyzing a problem. The audience composition for Trapper John, airing at 5 o'clock, is the same as the audience for Oprah Winfrey, airing at the same time.
We were in direct competition for the same audience. Oprah won. And it was time to us to reevaluate and to make a change. Was there another audience or that wasn't being serviced that we could try to counter Oprah with and bring up our ratings?
Why do you have problems selling that area? I mean, you tell me why. You can sell it in the morning, you can sell in the afternoon. Why is 5 o'clock such a big time?
We sell the kids for a cost per point. It's probably about a quarter to a fifth of an adult program area.
Okay.
So if you can sell it for...
Although a program appealing to younger viewers seemed like a logical way to counter Oprah, the decision is complicated by the fact that advertisers pay less for children's programming.
But it's not
Leslie is meeting with managers from sales and promotion to work out a compromise.
Besides doing just kids and teens ratings at 5 o'clock, we'd also be able to do some adult demographics.
There's not much product out there, though, right now that meets that criteria, is there?
Right. Well, we have the product that we own, wouldn't work as a transitional show. I mean, we know
We've
that.
tried
We've tried it, and we just feel that it's not strong product, so we would have to go out and buy. I know Punky Brewster is available, that we could start in January. Okay.
The Punky Brewster might be good coming out of kids going into the Family Ties with the young demos, but I don't know if we can necessarily make enough money even to pay for the show.
Well, I understand that, but let's say based on the November book, they're just not there.
Trapper John, and I know Quincy was successful a year ago in that time period, but it's not facing the same competition, particularly on CVB. And when you're getting...
The discussion went on for a long time, but eventually the decision was made to replace Trapper John with Punky Brewster.
Conga! That's my favorite! Oh, good.
It worked out really well. We ended up more than doubling our household rating, and we did some terrific numbers in the kids.
All right.
Let's try our hand at Leslie Savage's work. Suppose we have to choose between two hypothetical TV series: Action, a fast-paced adventure series, and Sitcom, featuring the warm-hearted humor of modern family life. When Action was originally shown, the age distribution of its viewers looked like this. This distribution is clearly not symmetric. Instead, it's skewed. One side is more spread out than the other. Action has many younger viewers, the bulge to the left, and only a few older viewers. Because the distribution trails off to the right, we say it's skewed to the right. In a skewed distribution like this, it's not easy to locate the center by eye. But since what we mean by center is the point that divides the distribution in half, we can say the center is about here at age 18. Half the viewers are younger and half are older. Overall, sitcom attracted an older audience. Again, the distribution is skewed, although this time the longer tail goes off to the left. It's said to be skewed to the left. Remember, it's the direction of the tail and not the bulge which determines which way we say a distribution is skewed. And what about the center? This time the midpoint of the distribution is here. About half these viewers are age 45 to 54 and older. Let's say the advertisers want to reach viewers between the ages of 18 and 54. Which show should we choose, sitcom or action? Well, sitcom clearly appealed to more people in the target age group. And assuming the price is right, sitcom will appear in our new fall lineup. There are some important factors to consider when constructing histograms. Perhaps the most important rule is that the classes, the categories on the horizontal axis, must be equal in width. That's because our eyes respond to the area of the histogram bars. If we keep the class widths equal, we can compare the heights of the bars without becoming confused by their area. Choosing the best way to divide the observations into equal classes requires good judgment. Hours of the day were obviously a good choice for constructing the lightning histogram, but it is not always so easy to decide what size each class should be. And if the classes are too small or too large, valuable information may be lost or hidden. For example, in this histogram of traffic on a busy street, it's obvious that most cars pass by between 8 and 9 o'clock. But we can't really pinpoint when rush hour peaks. The class size of 1 hour is too large. Now let's try a smaller class size, say half hours. That seems better. How about 15-minute classes? Better yet. We can see that rush hour is at its worst between 8:45 and 9. Can we get any closer? How about 5-minute classes? All of a sudden, the peak is harder to see. There are too many peaks. As classes get too small, the number in each class starts to look the same. This suggests a general rule for histograms. Classes that are too large or too small hide or lose information. Somewhere in the middle is the right class size, the picture that most clearly tells the story of the data. There's one more key feature we can learn about a distribution from a histogram. Its range, or how spread out the observations are. As an example of how much spread matters, let's talk about lowering healthcare costs.
There was a great deal of concern, particularly through the 70s and the early 80s, that the cost of healthcare was rising far higher than the rate of inflation, and that the federal government was being asked through this cost-plus system to pay more than perhaps they should have. The dilemma, though, was to come up with a way to pay hospitals in a fair way that related to the work that was done for a patient.
To standardize payments to hospitals, the federal government adopted a system called Diagnosis-Related Groups, or DRGs. In a nutshell, the idea is this. The government determines how long a patient is typically hospitalized for various treatments, and it pays a hospital claim on that basis, regardless of how long the individual patient actually stayed.
There are thousands of reasons why a patient might be admitted to a hospital. And it was necessary to come up with some sort of a classification system that took those thousands of different possibilities and grouped them into 470 relatively distinct categories.
Now, defining the DRGs so that they make both economic and clinical sense is a complicated statistical task. But let's look at two highly simplified cases. For the sake of discussion, say that the upper histogram represents treatment for heart failure, heart attack, shock, and so on, and the lower histogram, treatment for kidney stones. The shape of both is symmetric, and both center around 8 days. If we considered only shape and center, we would say the distributions are similar. But there's clearly an important difference between them. Kidney stone patients cluster tightly around the 8-day center, while heart failure victims may stay in the hospital from 1 to 20 days or more. We say the spread of the heart failure histogram is much greater than the kidney stone spread. If these histograms were real DRG data, we would find the spread in the heart failure distribution too great to be useful. So we try to break it up into several distributions, each for a more narrowly defined type of heart failure.